Howdy, PAP chemistry students. We're going to investigate the flame test lab. And first off, we're going to just do a little bit of explanation on what the Bohr model is. So here we have the energy levels. You have energy level 1, N equals 1, right? Energy level 2, energy level 3, 4, and 5. You'll notice that they converge higher that they get. And so that is a real thing. They will get closer and closer together. That's because the electrons will actually get closer and closer together the farther away they get from the nucleus. So in this type of diagram, the nucleus would be like right here, and so here would be the first shell of electrons. Okay, so really we're just looking at the difference between the distance between the energy levels. So what we're seeing here is when an electron is in its ground state, and we're going to actually say that the ground state here is at energy level 2. Okay, so that's going to be important because, and so anything that has a small jump is going to be and then as the electron goes from the ground state to the excited state, right, it's going to absorb that certain amount of energy. And then as it goes back from the excited state back down to the ground state, it will emit a photon at a specific wavelength. Now, just so happens that from energy level 3 to energy level 2, that's going to be red. Okay? Now, and just for, in this case, we're going to take a look at this one. So if an electron was in the ground state at energy level 2, and then it jumped up to the energy level 4, and then as it falls back down to the ground state, it will emit some green light. That has a little bit higher energy. Okay? So that is from energy level 4 to energy level 2. And now let's try the last one. You could probably guess energy level 5 to energy level 2 is going to be the greatest difference in energy. So it will be the highest energy of photon, which would be the purple light. Okay? So do a little demonstration right here. I have 3 photons, or 3 pieces of energy right here. I have red, green, and purple. So I am an electron, and I am standing on the ground. So I am in the ground state. And so when I receive a little bit of energy, I will become excited, and I moved up in energy. Now you will notice that I cannot exist somewhere in between. I cannot hover. I can only jump up to an excited state, and I have a little bit more energy, and then as I jump back down to the ground state, I give off my photon, my red photon. So same thing, I get a little bit more, and I have a little more energy, because green has a little more energy, so now I'm more excited. Okay? And then I jump down, back down to the ground state, and I throw my photon away. And then the purple one, of course, is when I get really excited. Woohoo! All right. And then I jump back down to the ground state, like so. All right, so you guys at least got to watch me jump around a little bit, but hopefully that lets you understand where electrons exist. They cannot exist somewhere in between. They have to exist on specific energy levels, like so. Okay? So now one thing that I think Crayola does a disservice to you, and they tell you that red, like red, orange, and yellow, are the warm colors, so we naturally think that they have more energy, but that is not true. Red has less energy than purple. Purple has the most amount of energy. Now think, you know that ultraviolet light can be harmful to you. That's what comes in the sun and can give you a sunburn. Well, that ultraviolet light, well, that's very close to violet light, which also has a lot of energy. Infrared light is not harmful to you, and so that is closer to the red light, and so it has less energy. So remember, small energy, big energy. Okay? So the colors you see here, where we're going from higher energy level down to energy level 2, this is called the Balmer series. And this is how we get visible light. Okay, this is the visible light. It comes down to energy level 2. So if it went down to energy level 1, there would be a greater difference in energy, so that would be the ultraviolet light. If it went down to energy level 3, there would be a smaller difference in energy, so it would be the infrared light. Okay? So this is the only way you can see light is anywhere, is whenever electrons fall down to energy level 2. So that would be helpful to be able to look at more flame test labs. So let's go ahead and see if we can excite some electrons. Okay, we're here to do our flame test lab, and what we're going to do is you have to use a Bunsen burner. So the first thing is to show you how to use one. First thing is you need to secure it yourself. So I will roll up my sleeves, and I will make sure I'm wearing my proper eye protection. Second thing is secure your area, and third thing is to secure your equipment. Secure yourself, secure your area, secure your equipment. So I'll make sure that all flammable objects are a foot away, and just make sure we're going to move stuff as far away as possible. And then I need to secure my equipment. So there are parts to a Bunsen burner that we need to check out. There's the hose, right? So we're going to look at the hose, make sure there's no cracks in it, and it's all squared away. If there are cracks, we'll take it out of service. And then we'll take a look at the Bunsen burner itself. So here, I just lit it, and it's still quite cool on top. So that's what's so great about it. Now the barrel turns here, and then the valve turns here. So the valve controls how much hydrocarbon, or how much gas is coming into the Bunsen burner. Now the barrel controls how much oxygen there is, because you need two things to make a flame. You need your fuel, and you need your oxygen. So this is to get the right mixture. So you'll see what I mean in a second whenever we light it, when we're getting the wrong mixture. So what you do first is you close this by looking straight down at it, and you're going to turn it all the way to the right, and it will close. No gas will come through. So we want some gas to come through, so we give it 2 turns to the right. Okay? And then we will close the barrel, looking down at the barrel right here, and we'll close it all the way by turning it to the right. Then place it, hook it up to the gas, and you'll need your striker. Now these strikers look scary, but they don't hurt you, as you can see. So they have a very high temperature. The embers have a very high temperature, but they have a very low energy, so they don't really conduct any heat toward your body. So well, that's what's so cool about them. So to turn on the gas, you need to turn the gas on here, and I can hear it. I can hear the gas coming on. So I'm going to light it just like so. All right. It takes a couple students to figure out how to use one of these. You have to push a lot of pressure towards it. So right now you'll see where we're getting a yellow flame, which is not very hot, not very good for heating. What we'll do is we need to increase the amount of oxygen that's coming in. This is called incomplete combustion, and so you are getting a lot of, you're releasing carbon monoxide, and it's not that great, and we want it to have complete combustion. So we're going to add some oxygen just by twisting the barrel here. You'll notice that this barrel is totally cool, all right? I can touch it, no problem. So you'll see that the flame turned blue, and now, but it's this tall. So that's not good. We want to lower it, and so we'll decrease the amount of gas. You see I'm changing this part right here. Now I'm going to fiddle with it to try to get the double blue cone. And as you can see, maybe on a black background, you might be able to see the double blue cone, or on a white background maybe. I know you're supposed to have them a foot away, but hopefully you can see maybe that. Alright, so you have your flame test lab printed out and ready to go. But there's your flame. Now the number one rule with an open flame is that you never turn your back to the flame. So we're ready to go. We are going to settle things the old scientific way, and we're going to burn stuff. We're going to take some, I have some coffee stirs that have been soaking in water, and then I have my dispose kit right here. So whenever I light something, I will notice the flame color, and then once I observe that flame color, see it's wet, so it's not burning yet. But even if I do light it, which you can tell it's lighting right now, I'll just place it in the water and it's extinguished. So no problem. So the first element on the list is lithium nitrate. Unfortunately, I cannot find any lithium nitrate in my stockroom right now, so we're just going to skip that one. It should have a nice pretty red color, but it's a bummer. So we'll move on to copper. So here is copper nitrate. Now, unfortunately, it absorbs a lot of water from the air, so it looks like a liquid. But it'll still work. So I turned out the lights. You may not be able to see very well, but I can still see. We have copper nitrate, and so as we place it into the flame, we get that color. All right. Now, as the liquid burns away, you'll see that the splint has the same color as what it was before. So that yellow color at the end was the splint. But what color was that? That looked green to me. So the next element on the list is going to be potassium nitrate. So we'll take this cover off. And so I just have a little bit of salt on the end of the stick. And so here it is. Okay. Next element on the list is calcium nitrate. So I have to be careful not to let any stuff drip down, because it likes to burn, it likes to melt and fall down into the Bunsen burner and get my Bunsen burner all nasty. So I don't want to do that. So that was the calcium nitrate. And this one is barium nitrate. Granular. Ooh. Very nice. And it's starting to go orange. That's because I'm burning the splint. So originally I think it was yellow. A yellow-orange. And then it went straight orange whenever I ran out of barium. Okay. And the next one is sodium chloride. Yes, sodium chloride. So this one's different. This is not sodium nitrate. This is sodium chloride. So we're going to see later on, we're going to compare sodium chloride and sodium nitrate together. Just give me a second and let's see that. Ooh. So this is everyday salt. Salt looks like this when you burn it. Don't try this at home. Alright, let's do strontium nitrate. Strontium nitrate is my favorite. So hopefully you saw a nice red flame. That's exactly how they get red fireworks, is they use strontium nitrate. And sodium nitrate. So you should compare this with that sodium chloride that we just did. Will that nitrate or the chloride, will that anion, that thing at the end, will that matter? You decide. Is it going to be the same color? What do you think? Ooh. Okay. And the last one. You can use flame tests to determine what a substance is, or at least to help narrow it down. So here's your unknown. What could it be? So I have extinguished the flame and made sure everything is safe and sound. No, nothing's on fire anymore. So then you have to do the analysis conclusion part. Few questions. Now, the first part says to describe the appearance of the overhead lights observed normally with your eye or with the spectroscope. I think I left that question off on Schoology because normally you are able to observe these through what we call a spectroscope right here. This is essentially a prism where the light goes through this hole right here, and some background light comes through here, and then you observe through here. And you should be able to see like the spectral lines through this spectroscope. So it's a little handy tool. Two difficulties that may occur during using a flame test. Well, you saw some colors had the same similar, compounds had similar colors, so that might be one difficulty. I bet you could think of another one. Why does sodium chloride and sodium nitrate have the same color or impart the same color? Well, we kind of went over that. Assuming only the metallic ions used in this lab, if a flame test produces a red flame, what ions are possibly present? I bet you could figure that one out. How could you distinguish between the ions that produced a red flame? What ions could be eliminated as possible ions if the flame test is red? Bet you could figure that one out. Consider red and violet light, which has a longer wavelength, the greater frequency, and which has a greater energy. Okay, so we covered the energy ones before. You can look back at your wave calculations to understand the others. That should be less than 4.1 or 5.1 or 5.2. And then what metal is present in the unknown solution? What do you think? Okay, so describe in terms of electron transitions how light is produced in a flame test. So what you should be looking at is that at the beginning of the video when I described those electron transitions, you should be basing that answer off of that. Okay? So hopefully you're good to go on your lab, and everything is going to be great. Have a great day.